Newton's law of universal gravitation states that every object attracts every other object with a force that for any two objects is directly proportional to the mass of each object. Newton deduced that the force decreases as the square of the distance between the centers of mass of the objects increases. The force of gravity between objects depends on the distance between their centers of mass. Your weight is less at the top of a mountain because you're farther away from the center of the earth. The law of universal gravitation can be expressed as an exact equation when a proportionality constant is introduced. The universal gravitational constant, big G, in the equation for universal gravitation describes the strength of gravity. The force of gravity between two objects is found by multiplying their masses, dividing by the square of the distance between their centers, and then multiplying this result by big G. Big G was first measured 150 years after Newton's discovery of universal gravitation by an English physicist, Henry Cavendish. Cavendish accomplished this by measuring the tiny force between lead masses with an extremely sensitive torsion balance. A simpler method was developed by Philip von Jolly. He attached a spherical flask of mercury to one arm of a sensitive balance. A 6-ton lead sphere was rolled beneath the mercury flask. The flask was pulled slightly downward. The gravitational force F between the lead mass and the mercury was equal to the weight that had to be placed on the opposite end of the balance to restore equilibrium. F, M1, M2, and D were all known, so the ratio G was calculated. G equals 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. The value of G tells us that gravity is a very weak force. It's the weakest of the presently known four fundamental forces. We sense gravitation only when masses like that of Earth are involved. Cavendish's first measure of G was called the weighing the Earth experiment. Once the value of G was known, the mass of Earth was easily calculated. The force that Earth exerts on a mass of 1 kilogram at its surface is 10 newtons. The distance between the 1 kilogram mass and the center of mass of the Earth is Earth's radius 6.4 times 10 to the 6 meters. From this you can calculate the mass of Earth. Mass of Earth equals 6 times 10 to the 24 kilograms. When big G was first measured in the 1700s, newspapers everywhere announced the discovery as one that measured the mass of Earth. Consider an imaginary butter gun for buttering toast. Melted butter is sprayed through a square opening exactly the size of one piece of square toast. The gun deposits a layer of butter 1 millimeter thick. Twice as far from the butter gun, the butter would cover twice as much toast vertically and twice as much toast horizontally. Since the butter has been diluted to cover 4 times as much area, its thickness will be 1/4 as much, or 0.25 millimeters. Butter spray travels outward from the nozzle in straight lines. Like gravity, the strength of the spray obeys an inverse square law. Twice as far from the gun, the butter is only 1/4 as thick. 3 times as far, it'll be 1/9 as thick. 1/9 is the inverse square of 3. When a quantity varies as the inverse square of its distance from its source, it follows an inverse square law. This law applies to the weakening of gravity with distance. It also applies to all cases where the effect from a localized source spreads evenly throughout the surrounding space. Other examples are light, radiation, and sound. The greater the distance from Earth's center, the less an object will weigh. An apple that weighs 1 newton at Earth's surface weighs only 0.25 newtons when located twice as far from Earth's center. When it's 3 times as far, it weighs only 1/9 as much. But no matter how great the distance, Earth's gravity never drops to 0. The gravitational influence of every object, however small or far, is exerted through all space.